This is 2.1, representing relations and functions. And so I'll just say, like, the really important thing with this section is to make sure you follow all the instructions. Okay, like like for those first ones, identify the domain and range of the given relation, then represent the relation using a graph and a mapping diagram. So that means there's 3 different, like, things you're supposed to do. And eventually we get to some that, or not necessarily that we get to some that have 4 things, but like when you get to like the quiz or the test, like there's like another step that goes with it. And so rather than doing like, oh, here's one problem and then here's another problem, like, and doing the 2 different sets of instructions, I will just like lump all 4 things into one. So I like would suggest that you like underline, like when you get to the test or the quiz, like everything that you're supposed to do, and like make sure you do them all in order so that you don't forget one, because it's like inevitable that people forget things that they're supposed to do. So all right, so they give you some ordered pairs. So this first one is -7, 4, 2, -5, 1, -2, and -3, 6. All right, so first we want to list the domain and range, and things only need to be listed once. So if there was a repeating one, we only list it one time. Now, I mean, if you do write it twice, that's not something I'm going to take off for until you get to the mapping diagram, because then your answers, well, you're going to end up probably getting the problem wrong because you're not going to see what's different about it. But with domain and range, we only write it once. It's nice if you write them in order numerically, but if you don't, again, not going to take off for that. So the domain are what values? The x values. So we just literally just write them down. So -7, -3, 1, 2. And a lot of times people just write them across in order, so like that's also fine. And then range are the what values? Y. So we have -5, -2, 4, and 6. So then the next thing it says to do is to represent the relation using a graph. So it doesn't need to be anything spectacular. You don't need to like get out graph paper. Like if you just enjoy graph paper and it's what you want to do, that's completely fine. But just, a little basic graph is fine. Our x values go to -7. Our y values go from -5 up to 6. So you can kind of just kind of wing it a little bit. I don't get out and like measure everything exactly, so it's just kind of an approximation. All right, so then you just graph each of these points individually. Don't connect them. Literally just put the dots on the graph. So -7, 4. 7. And then 2, -5. 1, -2. And -3, 6. Bless you. And then the last thing that we do is a mapping diagram. And so with that, we have an input column, an output column, and we just write the inputs are the domains, the outputs are the ranges. So again, I like these to be in order. I always circle them. So then you draw a line to match the input with its output. If an input had two outputs, then I would draw like two lines. Like if say -7 was repeated, I would draw two lines off of -7. Okay, and if like an output was repeated, like let's say 4 was repeated, then obviously there's going to be two lines that are going to it. So these don't have to have the same number of values in each column. The other common thing that I see that people do before we go on and like draw the lines is sometimes what people will do, rather than writing input and output, they just write domain and range like this. Don't write this because I don't want you to get confused. They'll just write domain and range. They won't do this. And then they'll say, but I put the domain and range. Okay, then where's your mapping diagram? You've got to have it as separate things. Okay, technically this is input, output in your mapping diagram. Domain and range is somewhere else. Like, yes, the values are the same, but again, you should have 3 separate distinct things. So just every year I say that, and inevitably someone still does it. So now you just draw the line. So -7 to 4, 2 to -5, 1 to -2, and -3 to 6. Any questions about how we do any of those? Okay. So, because we're going to end up doing some more with that in a little bit. I'm not going to do any more specifically out of that section at the moment, but we're going to do more stuff with it in a little bit. So tell whether the relation is a function. So they give you the mapping diagram, and you have to tell if it's a function or not. Do you remember from the notes what I said of how to tell if something's a function or not, or like what some of the different ways we can tell are?
The vertical line test.
The vertical line test will. So if it goes across and there's ever 2 points going across, what's another one? Yep. So if an input has more than one output, so if there's less inputs than there are outputs, you will know automatically. There could be the same, but there could be repeated ones. Okay, so like there could be like 2 different things that are getting repeated. If an output gets repeated, it is a function still. But if an input is repeated, it is not. So these ones are going to give you the mapping diagram. And you're going to just say if it's a function or not. So this one is -6, -4, -1, 2, 5, 2, 1, -1. And like they don't always write them in order, which is just kind of annoying, but you know, whatever. So from what you just told me, would this one be a function or not?
Yes.
Yes, why?
Each input has no more than one output.
Yep. Exactly. Let's see, number 12. I'm just gonna do it right here. Input, output. So they give you -1, 5, 4, 2, -1, -3, and then -1 is going to 2, -1 is going to -1, 5 is going to 4, and 5 is going to -3. So is this one a function?
No.
Why not? The inputs have more than one output, so this is not a function. And I don't know if I wrote this in the notes this way, but FNCT is another way to write function. It's just, I told, was it my Algebra 1 class yesterday, we were saying if something was a solution or not a solution, and I was writing SOLN for solution, and I was like, you're more than welcome to write the whole word out. If you want to shorten it, this is the way you can shorten it. This is how all my college professors did it, so I'm just like so used to it that it just like naturally just happens. So same thing with function. Just gonna put another example up here really quick that's not in your book, but input, output, -3, -2, 1, 4, 3, 2, and 4. And -3 goes to 2. -2 goes to 3. 1 goes to 2. And 4 goes to 4. Is this a function? Okay, so this one, the output, there's 2 outputs, but each input only has 1, so yes, it's a function. I guess technically up here I should have written function, not yes. So a lot of times what I will do is, going back to this problem up here, the 4th thing that I will add is tell if it's a function. And then I will say, like, I may say, like, explain why or something. And that way, if somebody, because sometimes people mix up if it's the input or the output, so there can't be more than one of, and so they'll tell me, like, the wrong thing. So at least I know, like, oh, okay, they just got it mixed up or whatever. So if I don't say explain, but you still want to, like, say why, that's fine, but you don't necessarily have to. So. But that would be the thing I would add on. So was this one a function? Okay, so yes, that one would be a function. So. All right, the next one say to tell whether the relation is a function, but this time they don't give you the mapping diagram. They give you a list of numbers like they did in number 6 up there. So number 18, 0, 1, 1, 0, 2, 3, 3, 2, 4, 4. So again, we have input and we have output. So I'm going to have y'all tell me this time what's going in each column. What's going in my input column? Okay, so what are they?
0, 1, 2, 3, 4.
Okay. And how about my output?
0, 1, 2, 3, 4.
Yep. And again, I'm not going to take off if you don't put them in order. It's just nice when I'm grading if they're all in the same order. All right, so 0 matches with 1. 1 goes with 0. 2 goes with 3. 3 goes with 2. And 4 goes with 4. So, is this a function?
Yes.
Yes. Because again, each input only has 1 output. All right, any questions about ones that look like that or anything with the drawing? Are we okay with graphing the points, domain and range, listing them separate, all that good stuff? Okay, cool. So then the next ones give you some graphs. So I'm just going to roughly graph the picture that's given to you in your book. If I can draw a straight line, that would be great. Okay. So this one they give you, it looks like this. And they want you to use the vertical line test to tell whether the relation is a function. So would this be a function?
Yes.
Okay, yes, because every point as I go across, there's only 1 point that's there. So this one would be a function. If you had something like, because they only do a couple of these in the book. So if you had something like this, would that be a function?
No.
No. It does not pass. There's more than one. Not a function. And then what about progressively getting smaller? Something like that.
No.
No. Okay, so then the last problems, there's some graphing in here. They say to tell whether the function is linear, then evaluate the function for the given value of x. So there's actually a whole thing of just graphing equations, y equals mx plus b. I trust that we know how to do that, so I'm skipping those. Like, I'm not giving you any of those. We know how to graph a line, right? Do I need to refresh on graphing lines? Okay, let's do one really quick just to make sure. I'll do 32. 32, y equals 1/2 x plus 2. Okay, so remember the equation of a line, y equals mx plus b. So when we get to the next set of problems, if it is linear, it should look like this, or it should be able to be put in a form that looks like this. If it can't, it is not linear.
So you start at 2 and then you go up 1/2.
Yep. So we have start at 2, and then rise over run to up 1, right 2, up 1, right 2, and you can also go down 1, back 2, and then just, connect your dots, and you graphed a line. So when they want you to tell if the function is linear, then you're going to see if it can be put in that form, and then evaluate the function for the given value of x. Regardless if it's linear or not, you're going to evaluate it. Just FYI, sometimes people get confused about that. So number 34, f of x equals x plus 15, and we're doing it for f of 8. So have y'all seen this notation before?
Yeah.
Okay. So just remember, f of x is just another way that we can write a function, and then when we put the 8 in, it's just wherever you see an x, you put an 8. So first of all, is this linear?
Yes.
Why is it not linear if it's not?
It's linear.
It is linear. Okay, why is it linear then?
It's the slope-intercept form.
Okay, so it's in the right form. Sometimes it confuses people, but just remember this is just a 1 that's here. Okay, so that's still your m value. So it's just up 1 over 1.
So as long as there's an x plus a number, it's
Yeah. So this one is linear. And then we just replace the equation, or the x with an 8. So we have f of 8 equals 8 plus 15, which would be 23. So evaluated, it would be equal to 23.
and just do the f of 8.
Yeah. The f of 8 just tells you that that's what's getting plugged in. Yeah, sometimes people then decide to go over and divide by 8 or some weird thing, and I'm always like, you're making more work for yourself.
Well, it looks like it's a variable.
It's pretty much f of 8 is just representing y.
Got it.
The f
so,
looks like it's a variable.
That's what I try to tell people. I'm like, it's just you're solving for a variable.
Yeah.
And
So
they're
just
just telling
ignore
you that evaluated at 8. So it's a function evaluated at 8.
Just remember to ignore the f like it doesn't exist.
Pretty
Not
much.
treat it like a variable.
All right, let's do another one. 36. F of x equals the absolute value of x plus 10. And it's for f of negative 4. So, would this be linear? Why?
Because there's an absolute value.
And do y'all know what an absolute value graph looks like?
No.
Maybe.
I don't know when you learned that, that's why I'm asking.
Ain't got a clue.
So an absolute value graph is a V.
Oh.
So, and this one in this case is just shifted up 10, so it would just look like, so if this is 10 here, it just looks like this.
Got it.
That's all that's happening with that. So you don't have to graph them, I'm just doing it to show you. So this is not linear. Doesn't graph a line. So then we're going to evaluate this equation for -4. So f of -4 is equal to the absolute value of -4 plus 10. And what is that? 14. So that becomes +4. So that's 14. Whoa. It's fine. All right. One more of these. 38 g of x. So you can, well, the common ones you'll see are either f, g, or h of x. They all mean the same thing.
Yeah.
It's just representing a function. Is equal to x cubed minus 2x squared plus 5x minus 8 for g of -5. So is this linear?
No.
Say hard pass.
Okay, no, it's actually a cubic function because the highest power is a 3. And I'm assuming you probably don't know what a cubic function looks like either. But it basically looks something like this.
I was gonna say squiggle.
It would pass the vertical line test, so it is a function, but it is not linear. So then we just plug in -5 for x. So g of -5 is equal to -5 cubed. Make sure you put parentheses around the number, especially when it's negative, so that you don't get confused about what's happening when you go to do the math. So -5 cubed is what?
-125.
-125. -2 times -5 squared would be what?
50.
-50. So the -5 squared becomes positive, giving you 25 times -2, so it's -50. And then 5 times -5,
-25.
-25, and then minus 8. So what does that give you as a final?
-208.
Yep, -208. Any questions about that stuff? No. Okay. So I'm gonna go ahead and give you your problems, and then we'll discuss. There's only a couple of them. 5, 11, 17, 21, and 35. Let me turn this off.